You guys help me out? What's the length of A? Okay. And the other one? Oh yeah, I could have done that one. Oh well. Lost my chance. So what's the angle? So you should impress your friends. You're like, I can find the angle between matrices. Can you? It's kind of shocking, really, isn't it? I mean, that's a weird idea, right? What do we get? 85 degrees. Well, obviously, I mean, you can tell from looking at them, right? Now, it's fairly obvious what's going on here, guys. If I gave you 4 vectors, right? If I gave you the vector 1, 2, 2 minus 4, and 1, 1, 1, 1, right? If these are 2 vectors in R4, right? These vectors, with respect to the usual Euclidean geometry of R4, are not perpendicular, and the angle between them is about 85 degrees. It's the same math. So what I want to talk to you guys about for the remainder of today is probably more important. Sorry. It's okay. But she is missing the good part. See, this is mostly just an example or two that I was trying to run through with you guys. I do have something new to define today, but it's really beautiful and simple and really quite interesting. And we'll do more with it this semester as we go on. And that's the idea of orthogonal and unitary transformations. Well, let's say matrices. Or transformations. Excuse me, that onion got me. Or transformations. I mean, oh man, goodness gracious. Whew. I'm not sick, it's just, she's got like some the pico de gallo in here, you know, and all right. So, think about a transformation, all right, that goes from, say, Rn to Rn. I'll start with the orthogonal, okay? I'll start by trying to describe to you what an orthogonal transformation is. The idea of an orthogonal transformation is the following. If we take the dot product of t of x and t of y, all right? And here x and y are, you know, vectors in Rn. If this is an orthogonal transformation, all right, by definition for us, that's going to be equal to x dot y. Let me put that in words. Orthogonal transformation preserves dot product between vectors. What's the significance of that? How is the length of t of x related to the length of x? Tell me how. It's proportional. That's true, but we can be stronger than that. T of x dot t of x is what? This is by definition, essentially, the length of t of x, right? Squared. Which is the length of x squared. So an orthogonal transformation preserves the dot product between vectors, which implies, since these are both non-negative, right? This implies that the length of t of x is the length of x. So it preserves vector length. Cool, right? What about the angle between vectors? How is the angle defined? It's essentially defined by cosine of theta is what? If we talk about theta being the angle between x and y, it's equal to what? That's x dot y divided by what? Length of x, length of y, right? But check it out. If this is an orthogonal transformation, this is equal to what? This is equal to t of x dot t of y, yeah? And by the calculation above, that's the length of t of x and the length of t of y. So that is what? That is the angle. So this right here is the cosine of theta, let's say tilde, where theta tilde is as pictured. Here's t of y, here's t of x, here's your theta tilde, the angle between those guys. So the cosines are the same. In fact, it follows then the angles are the same. So orthogonal transformation preserves what? Length of vectors, angle between vectors. So what's an orthogonal transformation going to do to a shape? If you think about mapping a shape under an orthogonal transformation, what's it going to do to the shape? Is it going to bend it and twist it and change its shape? Yeah, all the relative geometric features to the shape are going to stay the same. Well, there is one thing that could happen, all right? That's not entirely kind of the same. So this right here is a characterization of a linear transformation, but we'd like to define a matrix, an orthogonal matrix. So definition, orthogonal matrix is matrix, the standard matrix, okay? Of what? Of an orthogonal transformation. So how's that go? So in other words, it's t of x. We'll usually use an r for orthogonal transformation matrix. So let's say t of x is equal to rx. So I'm saying the standard matrix of t, I'm denoting it by r just for the sake of our discussion here, okay? Excuse me. So what is this condition? T of x dot t of y equal to x dot y. And this holds for all x and y. What's this condition look like for the matrix R? We get what? We get Rx dotted with Ry equals to x dot y, right? How do we rewrite that in terms of matrix multiplication? What is the dot product? It's what? The transpose times the second thing, right? So this is Rx transpose times Ry equals to x transpose times y. Okay, let's rewrite the sock shoes, right? So this is x transpose R transpose R times y is equal to x transpose times the identity matrix times y. I put the identity matrix in there to make a point. Do you guys know what happens? If you look at EI transpose times A times EJ, what's that give you? Let me walk you through it. It's been a little while since we did this kind of stuff. But what's this? This is column J of A, right? So what happens when you take column J of A and multiply it by EI transpose? It picks off the ith component of that column. So this is just a sneaky way of projecting out the ijth component of A. So if this identity here holds for all x and y in Rn, then we can just put x and y equal to the standard basis vectors, and that will give us that the component of R transpose R is equal to the component of I for all I and j. So it implies that, in fact, R transpose R is equal to I. So this right here, guys, is how we actually like to think of orthogonal matrices. That's the definition I usually stick with once we get past this introductory spiel. So an orthogonal matrix is one which satisfies R transpose R equals to I. Excuse me. Questions? Yeah.
So how did you choose to stick an I between the X transpose and the Y? I don't know.
Oh, well, this is the identity matrix, right? So, like, you know, I can put it anywhere.
Okay.
It's like, it's everywhere, man. It's,
Yeah.
but more to the, I mean, my reason for doing that was so that when I get to here, I can essentially cancel the Y and cancel the X transpose on both sides. The only reason I'm allowed to do that again is because this holds for all X and Y. So by selecting the standard basis, I'm able to say the ijth component of R transpose R is equal to the ijth component of the identity matrix. If that holds for all I and j, we get equality here. What's the inverse of an orthogonal matrix?
Oh, it's the
Transpose. Yeah. This is nice. How about the columns of an orthogonal matrix? Can you say anything about those to me? If R is equal to, say, V1, V2, Vn, what can you say about these column vectors? What is the meaning of R transpose R? So what's a typical element here? It's Vi transpose times Vj, right? That's the ijth component of this product. But this is equal to the identity matrix, right? Which has typical delta ij as the component, right? So this gives us that Vi dot Vj is Kronecker delta ij. In other words, the columns of an orthogonal matrix are orthonormal. There's another way you can look at this. This calculation is reversible. If you want to build an orthogonal matrix, what do? Yeah, you take an orthonormal basis and glue it together, and that gives you an orthogonal matrix. So what this means is if we have an orthonormal basis, the inverse matrix to the basis is really easy to calculate. We just transpose it. We don't actually have to invert it like you guys have seen for other things, right? This is wonderful. I think we don't have enough time today to do the other thing, but I'll just tell you this. The unitary matrices are simply ones that preserve the complex inner product. So like, instead of having this, you have u of x inner product with u of y equals to inner product of x and y. When you look at what that means in terms of matrices, it ends up giving you that the matrix of u, which I need to come up with some other letter for, let's say A, it gives you that A times goodness gracious, A transpose times, well, I guess I better work, I may not try to, anyway, you can go through a similar calculation and we'll come to a definition of unitary. I think unitary is just this though, A dagger A equal to the identity matrix, but I'm a little bit, I'd like to work through that with you maybe some other day. I think you have some questions about unitary matrices, so in the meantime, just look in Shores. He has a definition in there. You can find it. But they're the complex analog of orthogonal matrices. They preserve the complex inner product. Anyway, we're now 10 minutes over. I started 5 minutes late, so I think we're about right. We should stop. Sorry.